You are listening to the Data Factory Blueprint, your guide to Azure data integration. Like and subscribe to keep up to date on our latest audiobooks. The Data Factory Blueprint, your guide to Azure data integration. Chapter 1, The Data Deluge and the Need for a Factory. 1.1, The Ubiquity of Data, a modern challenge and opportunity. Imagine a world without statistics, without sales figures, without customer feedback, or even without your smart device knowing your preferred coffee order. That world is unimaginable today because data permeates every facet of our lives. Businesses, governments, scientific institutions, and individuals are all generating, consuming, and relying on data at an unprecedented scale. Think about a typical day. Your smartphone tracks your steps and sleep patterns, recording health data. Your car's navigation system logs your routes and traffic conditions. Every online purchase creates a record of transactions and preferences. Social media interactions generate billions of individual data points on engagement and trends. Sensors in factories monitor machinery performance, generating operational telemetry. Hospitals digitize patient records and medical imaging, building vast healthcare datasets. This isn't just about sheer volume. It's also about the velocity at which data is created and the variety of its forms. Data streams in at breakneck speeds from diverse sources, structured rows in databases, unstructured text files, social media feeds, sensor readings, images, and videos. This explosion of data is often summarized by the 3 V's. Volume, the sheer amount of data being generated and stored. We're talking petabytes and exabytes, far beyond what traditional systems were designed to handle. Velocity, the speed at which data is generated, collected, and processed. Think of real-time stock market data or sensor readings from a high-speed production line. Variety, the different types of data, structured, semi-structured, unstructured, and their differing formats coming from a multitude of sources. This data deluge, while presenting an enormous opportunity for insights, also brings significant challenges. How do you collect this scattered, messy data? How do you make sense of it when it's in 1,000 different formats, scattered across different systems and locations? How do you ensure it's accurate, consistent, and up-to-date? And critically, how do you get it into a format and location where it can be analyzed and used to make better, faster decisions? Without effective tools and strategies, this data deluge can quickly become a data swamp, a vast, unusable collection of information that hinders rather than helps. This is precisely where the concept of a data factory becomes indispensable. 1.2 From raw materials to refined insights, the essence of ETL/ELT. Before we dive into Azure Data Factory, it's crucial to understand the fundamental processes it facilitates. These processes are universally known as ETL and ELT. They represent the journey of raw data from its origin to its destination, where it becomes useful information. ETL stands for extract, transform, load. It's been the cornerstone of data warehousing for decades, a methodical approach to preparing data for analysis. Let's break it down using an analogy. Imagine running a factory that takes raw timber and turns it into finely crafted furniture. Extract, this is the first step, where raw data is pulled from its source systems. In our furniture factory, this is like collecting the felled trees from the forest. This could be data from an operational customer database, a flat comma-separated file on an old server, or even a stream of events from a mobile application. The data is often in its original, raw, and sometimes messy state. Transform. Once extracted, the data isn't usually in a perfect state for immediate use or analysis. It needs to be cleaned, standardized, aggregated, and reshaped. This is the heart of the ETL process. In our factory analogy, this is where the timber is debarked, sawed into planks, planed smooth, and perhaps treated or stained. This might involve cleaning, removing duplicates, correcting errors, e.g., misspelled city names, invalid dates. Normalizing, standardizing formats, e.g., ensuring all dates are in one consistent format, converting units. Aggregating, summarizing data, e.g., calculating total sales per day from individual transaction records. Joining, combining data from multiple sources, e.g., linking customer data with their purchase history to understand buying patterns. Filtering, removing irrelevant data that isn't needed for the target analysis. This transformation typically happens on an intermediate server or processing engine before the data reaches its final destination. Load. Finally, the transformed data is loaded into a target system, typically a data warehouse or data lake, where it's organized and ready for reporting, analysis, and business intelligence tools. In our factory, this is like assembling the prepped planks into a finished table or chair, then stocking it in the warehouse, ready for distribution. ELT stands for extract, load, transform. While it sounds similar, the order of operations is subtly but significantly different, especially in the modern cloud era. Extract, same as ETL, data is extracted from source systems. Our timber is still collected from the forest. Load. The key difference here is that the raw, extracted data is loaded directly into the target system, often a cloud-based data lake, a massive, inexpensive storage repository for raw data, or a scalable data warehouse. This is like dumping all the raw, unprocessed logs and timber directly into a very large, flexible yard within your factory premises. The cloud provides immense storage and compute power on demand, making this physically practical and cost-effective. Transform. Only after the raw data is loaded into the high-performance target system are the transformations applied. This leverages the processing power and scalability of the target system itself, rather than a separate, intermediate server. Using our analogy, this is like having incredibly powerful, mobile logging and milling equipment within your large storage yard, allowing you to process the timber in place, on demand, and in parallel, without moving it to a dedicated processing line elsewhere. Why the shift to ELT in the cloud? Cloud platforms offer virtually limitless storage and elastic computing power, meaning you can instantly scale up or down as needed. This means you can load vast amounts of raw data cheaply and quickly into a cloud storage solution like a data lake. Then, you only pay for the compute resources when you need to transform it, typically using powerful cloud-native analytical engines like Databricks or Synapse Analytics, which can process data directly within the lake. This load-first, transform-later approach provides greater flexibility, can be faster for very large datasets, especially when transformations are complex, and preserves the raw data for future needs or different transformation requirements. It empowers data scientists and analysts to work directly with the raw data if needed. Whether ETL or ELT, the core objective remains the same: to turn raw, disparate data into actionable insights. And this is precisely the mission of Azure Data Factory. 1.3, the cloud transformation. Why managed services like ADF shine? For decades, organizations built their ETL or ELT pipelines using on-premises software or custom-coded solutions. These approaches, while effective, came with significant drawbacks. Infrastructure costs. You needed to purchase and maintain powerful servers, storage arrays, and complex networking equipment. This was a hefty upfront investment and incurred ongoing operational expenses for power, cooling, and space. Scaling challenges. What happens when your data volume suddenly doubles? Scaling up on-premises infrastructure is a slow, expensive process, often leading to over-provisioning, buying more than you need, just in case, or under-provisioning, not enough processing power when you need it most. This could result in bottlenecks and missed insights. Maintenance overhead. Keeping the underlying operating systems and ETL software updated, patching security vulnerabilities, managing backups, and troubleshooting hardware failures consumed valuable IT resources and personnel time. This distracts from core business objectives. Complexity of connectivity. Connecting to diverse data sources, especially those outside your internal network, like SaaS applications or partner systems, could be a logistical nightmare involving firewalls, VPNs, and complex network configurations. The advent of cloud computing fundamentally changed this paradigm. Cloud providers like Microsoft Azure offer a vast array of services that abstract away the underlying infrastructure. Instead of buying individual servers, you consume computing power on demand. Instead of managing complex databases, you use managed database services where the provider handles the operational burden. This shift to cloud-based platform as a service, PaaS, or software as a service, SaaS, models transformed data integration. Enter Azure Data Factory, your cloud integration hub. Azure Data Factory, ADF, embodies the best of cloud-native data integration. It's a fully managed, serverless, cloud-based ETL and ELT service provided by Microsoft Azure. This means no servers to manage. Microsoft handles all the infrastructure provisioning, patching, scaling, and maintenance. You don't need to worry about server uptime or capacity planning. You simply focus on designing your data pipelines. Elastic scalability. ADF automatically scales its compute resources up and down based on your workload. If you suddenly need to process petabytes of data, ADF can handle it by allocating more resources dynamically, without you needing to do anything manually. When the workload completes, resources are released, optimizing cost. Cost effectiveness. You pay only for what you use. There are no upfront hardware costs, and you're not paying for idle server time. This pay-as-you-go model makes it incredibly efficient, especially for fluctuating workloads. Rich connectivity. ADF boasts an impressive array of built-in connectors to hundreds of data sources and destinations. These include other services within Azure, like Azure SQL Database, Azure Data Lake Storage, Azure Synapse Analytics, services outside of Azure, such as Amazon S3, Google Cloud Storage, Oracle databases on-premises, popular SaaS applications, like Salesforce, HubSpot, and various file systems and protocols. This makes it a truly universal data orchestrator, capable of bridging diverse environments. Visual development. ADF provides a highly intuitive, drag-and-drop user interface known as the Azure Data Factory Studio. This visual environment allows you to design complex data pipelines with minimal to no coding for many common tasks, making it accessible to a broader range of data professionals, including those with less programming experience. Robust monitoring and orchestration. It offers powerful tools to schedule, monitor, and manage your data pipelines. You can set up triggers to run pipelines at specific times in response to events like a new file arriving or on a recurring basis. Comprehensive monitoring dashboards allow you to track the status, performance, and success of your data flows, ensuring data moves smoothly and reliably. Analogy. A highly automated, self-managing data factory. Imagine you run a massive food processing plant. In the old days, you'd have to buy all the machinery, hire technicians to maintain it, set up the conveyor belts, and manually tweak settings for every new product. It was a huge undertaking requiring significant capital and expertise. With Azure Data Factory, it's like you've moved your entire operation into a state-of-the-art, fully automated, and highly flexible building that someone else owns, maintains, and continuously upgrades. You simply tell it, here's where the raw ingredients are, your data sources, whether they're on your farm or across the country. Here's how I want them processed, and combined, your transformations peel, slice, mix, cook. And here's where I want the finished products delivered, your data destinations, a warehouse, a store, an analytics dashboard. The building systems automatically allocate the machines, adjust the conveyor speeds dynamically, handle minor breakdowns, and instantly expand its capacity whenever you need to process more ingredients. You only pay for the ingredients processed and the actual electricity consumed by the machines you used. This is the tremendous power and convenience that Azure Data Factory brings to the world of data integration. In the chapters that follow, we will pull back the curtain on this incredible data factory, exploring its core components, understanding how they work together, and learning how you can leverage them to transform your own data challenges into powerful, actionable insights. Chapter 2, Welcome to Azure Data Factory, your cloud integration hub. 2.1, Unpacking the Data Factory metaphor. In the previous chapter, we introduced Azure Data Factory, ADF, as a data factory, a place where raw data is transformed into refined, usable information. Let's delve deeper into this analogy to understand how ADF operates. Imagine a highly automated modern manufacturing facility. This factory doesn't just make one product. It's designed to process many different raw materials and produce various finished goods. The factory building, this is Azure Data Factory itself, the cloud service container, the managed environment provided by Microsoft. You don't build the building, you rent space and use its advanced machinery. Assembly lines, pipelines. Within this factory, there are various assembly lines. Each assembly line is a sequence of steps designed to produce a specific product. In ADF, these are called pipelines. A pipeline is a logical grouping of activities that perform a unit of work. For example, one pipeline might be an assembly line for taking sales data from your CRM, cleaning it, and loading it into a data warehouse. Another might be for converting log files into a summary report. Individual machines, activities. Along each assembly line, there are individual machines, each performing a specific task. One machine might cut materials, another might assemble components, and a third might package the final product. In ADF, these are called activities. An activity represents a specific processing step within a pipeline. Examples include an activity to copy data from one place to another, an activity to run a piece of code, or an activity to initiate a transformation process. Raw materials and finished goods, datasets. For any factory, there are raw materials that enter the assembly line and finished goods that exit it. In ADF, these are called datasets. A dataset is simply a named reference or a pointer to the data you want to use or create. It defines the structure and location of your data, whether it's incoming raw data, e.g., a CSV file in cloud storage, or outgoing processed data, e.g., a table in a database. Connection points, linked services. For your factory to operate, you need connections to suppliers for raw materials and connections to distribution centers for finished goods. You also need connections to specialized tools or services, like a power grid, a water supply, or a network of robots. In ADF, these connection points are linked services. A linked service defines the connection information required to connect ADF to external resources. This could be a connection to an Azure storage account, an Azure SQL database, an on-premises Oracle database, or even a different cloud provider's storage. It's akin to having a configured truck route and loading dock for a specific supplier. The workforce and engines integration runtimes. Even in an automated factory, there's a workforce or underlying engines powering the machines. Sometimes it's a general-purpose team, sometimes a specialized one for heavy lifting or secure operations. In ADF, this concept is represented by integration runtimes, IRS. An integration runtime is the compute infrastructure that Azure Data Factory uses to execute activities. It determines where the data movement or compute activity happens. There are different types of IRS for different scenarios, such as moving data between Azure services, connecting to on-premises data sources, or executing complex data flows. By understanding these core components, you begin to see how ADF acts as that central orchestrator, bringing together diverse elements to streamline your data journey. 2.2. The core components of Azure Data Factory. Let's look at each of these components in a bit more detail. Pipelines. A pipeline in ADF is the fundamental unit of work. It's a logical flow of activities that you define to achieve a specific data integration task. Think of it as a workflow diagram. A pipeline might contain one or many activities chained together. For instance, a pipeline could first copy a file from an SFTP server, then invoke an Azure Databricks notebook to process that file, and finally send an email notification upon completion. Pipelines can run on a schedule or in response to specific events, or even manually when needed. Activities. An activity is the action or task performed within a pipeline. ADF offers a rich library of pre-built activities to handle common data integration scenarios. These broadly fall into three categories: data movement activities. The most common is the copy activity, which is used to move data between data stores. It can copy data from almost any source to any destination supported by ADF. Data transformation activities. These activities perform operations on data. Examples include data flow activity for complex, code-free data transformations at scale, Databricks notebook activity to execute powerful Spark notebooks for advanced analytics and machine learning, stored procedure activity to run a stored procedure in a database, HD Insight Hive Pig Spark activities to run big data queries on Hadoop clusters, control flow activities. These are used to manage the flow and logic of your pipeline. Examples include for each activity to iterate over a collection of items. If condition activity, to execute different paths based on a condition. Wait activity, to pause the pipeline for a specified duration. Web activity, to call a REST API endpoint. Lookup activity, to retrieve data from an external source for use in subsequent activities. Datasets. A dataset is a named data structure that points to the data you want to use or produce. It's essentially a pointer and a schema. For example, you might create a dataset named Sales Data CSV that points to a specific CSV file in your Azure Blob Storage account and defines the columns and their data types within that file. Another dataset, Customers Table, might point to a specific table in your Azure SQL database. Datasets don't contain the data itself. They merely describe its location and structure, allowing activities to read from or write to them. Linked services. Linked services are the connection strings that Azure Data Factory uses to interact with external resources. They hold the connection information, which can include server names, database names, authentication credentials, and more. For example, a linked service named Blob Storage Connection would contain the details needed to connect to your Azure Blob Storage account, while SQL Server Connection would hold the credentials and server name for your Azure SQL database. You need a linked service for every data store or compute resource that your pipeline interacts with. Integration Runtimes, IRS. The Integration Runtime, IR, is the compute infrastructure that ADF uses to connect to, move, and transform data. It's the engine behind the scenes. There are three main types of IRS. Azure Integration Runtime. This is the default and fully managed IR that handles data movement between cloud data stores and dispatches activities to various compute services like Azure SQL Database, Azure Synapse Analytics, or Azure Databricks. It requires no setup or management from you. Self-hosted integration runtime. When your data is located on premises, inside your corporate network, behind a firewall, or in a virtual private cloud, the Azure IR cannot connect directly. For these scenarios, you install a lightweight piece of software called the self-hosted IR on a machine within your private network. This IR securely connects to ADF over an outbound HTTPS connection, acting as a secure gateway that can reach your on-premises data stores. Azure SSIS Integration Runtime. This specialized IR is designed to lift and shift existing SQL Server integration services, SSIS, packages to Azure. It provides a fully managed environment to run your SSIS workloads in the cloud. Triggers, while not typically categorized as a core component, in the same vein as pipelines or linked services, triggers are fundamental to making your data factory truly automated. A trigger defines when and how a pipeline execution should be started. You wouldn't manually start your assembly line every time you needed a product. You'd have a system to kick it off. Common types of triggers include schedule trigger, to run a pipeline at a specified time and recurrence, e.g., daily at 2 a.m. hourly. Tumbling window trigger, to run a pipeline at a specified time interval, maintaining the state of the windows being processed. Useful for historical data processing. Event-based trigger, to run a pipeline in response to an event, such as a new file arriving in Azure Blob Storage or an existing file being deleted. 2.3 How these components work together. A simple flow. Let's consider a practical scenario for a simple data flow using these components. You have daily sales data files, CSV format, dropped into a specific folder in your Azure Blob Storage, and you want to copy them into a table in your Azure SQL database. Linked services. You'd first set up two linked services, one for your Azure Blob Storage account, providing the connection details and authentication. One for your Azure SQL database, providing the server name, database name, and credentials. Datasets. Next, you define two datasets. An input dataset, daily sales CSV, pointing to the specific folder and file pattern sales CSV in your Azure Blob Storage using the Blob Storage linked service. This tells ADF where to find the raw sales data. An output dataset, sales table, pointing to the specific sales table in your Azure SQL database using the SQL database linked service. This tells ADF where to write the process data. Pipeline, you would then create a new pipeline. Inside this pipeline, you would drag and drop a copy activity. You would configure the copy activity. Set the source of the copy to your daily sales CSV dataset. Set the sync destination of the copy to your sales table dataset. Specify the integration runtime. In this Azure to Azure scenario, the default Azure IR would be used automatically that will execute this copy operation. Trigger. Finally, to automate this, you would create an event-based trigger. This trigger would monitor the specific folder in your Azure Blob storage. When a new sales CSV file appears, the trigger would fire. The trigger would then initiate the execution of your pipeline, which in turn runs the copy activity. The copy activity, leveraging the Azure integration runtime, would then use the linked services to connect to blob storage, read the new sales data file, as defined by daily sales CSV, and efficiently write that data into the sales table in your Azure SQL database, as defined by sales table. All orchestrated and managed by Azure Data Factory. 2.4 The Azure Data Factory Studio, your control panel. While this book focuses on conceptual understanding rather than step-by-step clicks, it's important to know that most of what we've discussed, creating pipelines, linked services, datasets, activities, and triggers, is done visually through a web-based interface called the Azure Data Factory Studio. Think of the studio as your factory's control room. It provides a visual designer for dragging and dropping activities to build pipelines, editors for configuring linked services and datasets, monitoring dashboards to track the status and performance of your pipeline runs, tools for managing your factory's code or definitions, and deploying changes. This intuitive interface significantly lowers the barrier to entry for data integration tasks, allowing you to focus on the logic of your data flow rather than the underlying infrastructure. 2.5 Key benefits of using ADF, revisited and reinforced. By now, the advantages of using a cloud-native service like Azure Data Factory should be even clearer. It provides agility and speed. Quickly build and deploy data pipelines without provisioning infrastructure. Scalability automatically handles varying data volumes and processing needs from megabytes to petabytes. Cost efficiency. A pay-as-you-go model means you only pay for the resources consumed during actual pipeline execution. Reduced operational overhead. Microsoft manages the underlying infrastructure, security patching, and maintenance, freeing up your team. Broad connectivity. Connects to virtually any data source or destination, on-premises or in the cloud. Empowerment. Allows data engineers, analysts, and developers to build robust data solutions with a visual, intuitive interface, reducing the need for extensive custom coding. Robust monitoring. Built-in tools provide insights into pipeline performance and health, crucial for managing complex data operations. Azure Data Factory truly provides the blueprint and the tools to build a sophisticated and efficient data integration system in the cloud, putting you in control of your data deluge. In the next chapter, we'll dive deeper into the individual building blocks of ADF, linked services, datasets, and pipelines, and start to explore how you configure them. Chapter 3. Building blocks. Linked services, datasets, and pipelines. In Chapter 2, we took a bird's-eye view of Azure Data Factory, introducing its key components. Now, it's time to roll up our sleeves and explore the foundational pieces individually. Linked services, datasets, and pipelines. Understanding these three intimately is crucial, as they form the very DNA of any data integration solution you build in ADF. 3.1 Linked services. The keys to the kingdom. Think of your data factory as a locked vault, and your external data sources, like databases, storage accounts, or web services, as other vaults scattered around the world. To get data from one vault to another, you need a key that grants you access. In Azure Data Factory, that key is a linked service. A linked service is essentially a connection string. It defines the information needed for Azure Data Factory to connect securely to an external resource. This resource could be an Azure service, an on-premises database, a file server, or even a third-party cloud application. It contains all the necessary connection details, such as server names or URLs, the address of the resource. Authentication methods, how ADF should prove its identity to the resource, e.g., username and password, service principal, managed identity, access keys. Other relevant parameters. Depending on the resource, this might include database names, port numbers, or specific API keys. Why are linked services crucial? Separation of concerns. Linked services separate the connection details from the data pipeline logic. This is a best practice in software development. Imagine if every activity in your pipeline that needed to connect to a database had to contain the database server name, username, and password. If the password changed, you'd have to update dozens of activities. With linked services, you update the connection information in one central place. Reusability. Once you define a linked service for, say, your Azure SQL database, any dataset or activity within that data factory can reuse that same linked service to connect to that specific database. This saves time and reduces errors. Security best practices. Linked services are engineered with security in mind. They integrate deeply with Azure's security features. Secure credential storage. ADF encrypts and securely stores credentials within the linked service definition. Azure Key Vault integration. For production environments, it's highly recommended to store sensitive credentials, like passwords or API keys, in Azure Key Vault. Your linked service can simply reference the secret stored in Key Vault, ensuring that sensitive information never directly resides within the data factory definition. This enhances security and simplifies credential management. Managed identities. ADF can use managed identities, a feature of Azure Active Directory, to authenticate to other Azure services. This eliminates the need to manage credentials entirely, as Azure automatically handles the identity lifecycle. It's a highly secure and recommended authentication method. Examples of linked services. You'll create linked services for almost every external system your data factory interacts with. Some common examples include Azure Blob Storage linked service. Connects to your Azure Blob Storage account, allowing you to read from or write to blob containers and files. Azure SQL Database linked service. Connects to a specific Azure SQL database, enabling read-write operations on tables and views or execution of stored procedures. SFTP linked service. Connects to an SFTP server, typically used for exchanging files with external partners or legacy systems. Azure Synapse Analytics linked service. Connects to your Synapse workspace or dedicated SQL pool for data warehousing and analytics. Amazon S3 linked service. Illustrates ADF's cross-cloud capabilities, allowing connectivity to Amazon's popular object storage service. In essence, a linked service provides ADF with the address book entry and authentication credentials required to communicate with external data sources and compute resources. 3.2 Datasets, your data's passport. If a linked service is the key to a vault, a dataset is like a passport for your data. It tells Azure Data Factory where your specific data resides within a linked service and what structure that data has. A dataset is a named reference to structured data that you intend to use as either an input source or an output sink for an activity within a pipeline. Datasets do not contain the actual data. They are metadata that describe location, which linked service to use, and the specific path or object within that linked service, e.g., a particular file path, a specific table name, a container name. Format. The format of the data, e.g., CSV, JSON, Parquet, AVRO, ORC, Excel, text files with delimiters. Schema, optional but recommended. The column names, data types, and sometimes even the length or precision of the data within the source or target. While often optional, defining a schema up front or allowing ADF to infer it helps ensure data integrity and allows for more robust operations. Why are datasets important? Abstraction. Datasets abstract the physical details of data storage from the activities that operate on them. An activity, like a copy activity, doesn't need to know the specific path to a CSV file. It just needs to know which dataset to use. If the source file location changes, you update the dataset, not every activity that uses it. Structure and type definition. Datasets help define the expected structure of your data. This is particularly useful in transformation activities, as it allows ADF to understand how to read and interpret the data, even if it's arriving in a complex format. Readability and maintainability. Giving your datasets meaningful names, e.g., input processed data CSV, output processed customer data SQL, makes your data factory solutions easier to understand and maintain. Relation to linked services. It's critical to understand that a dataset always relies on a linked service. You can't define a dataset without first having a linked service that tells ADF how to connect to the storage or database where that data resides. The linked service provides the general connection information. The dataset provides the specific detail about the data's location and structure within that connection. Types of data and formats. ADF supports a vast array of data sources and target formats. Whether your data is in traditional relational databases, modern NoSQL stores, data lakes, or SaaS applications, ADF can often connect to it. Common file formats you'll define datasets for include delimited text, CSV, TSV, simple, common for tabular data, JSON, flexible, often used for semi-structured data from APIs or logs, Parquet, a columnar storage format optimized for analytical queries, highly efficient for big data, Delta Lake, an open-source storage layer that brings ACID, atomicity, consistency, isolation, durability, transactions to data lakes. Binary, for copying files as is without parsing their content. You can create datasets that point to a single file, a folder containing multiple files, often using wildcards for patterns, or a specific table view in a database. 3.3 Pipelines, the assembly lines of data. Now that we have our connections, linked services, and our data definitions, datasets, we can construct the actual workflows that move and transform the data. This is where pipelines come in. A pipeline in Azure Data Factory is a logical grouping of activities that together perform a unit of work. Think of it as the sequence of steps on an assembly line. Each step activity performs a specific task, and they are orchestrated in a defined order. Core structure of a pipeline, activities. As discussed in Chapter 2, these are the individual tasks within your pipeline. Examples include copy activity to move data, data flow activity for visual data transformations, lookup activity to retrieve a single row or value for use in a later activity, for each activity, to iterate over a collection of items, e.g., process each file in a folder, execute pipeline activity to call another pipeline, allowing for modular and reusable designs, stored procedure activity to run a predefined procedure in a database. Control flow elements. Pipelines aren't just a straight line of activities. They can incorporate logic to handle different scenarios, dependencies. Activities can be linked together with success, failure, completion, or skip dependencies. This dictates the order of execution. For example, activity B only runs if activity A succeeds. Batching looping for each. Process multiple items in a collection. Conditional logic, if condition, switch, execute different branches of activities based on conditions. Branching, allow multiple activities to run in parallel. Parameters. Pipelines can be parameterized to make them dynamic and reusable. Instead of hard-coding a file name or a database table name into an activity, you can define a pipeline parameter, e.g., file name, table name. When the pipeline runs, you pass specific values for these parameters. This allows you to use the same pipeline for different business cases without modifying its core definition. How activities link together, dependencies. The power of pipelines lies in their ability to define dependencies between activities. After an activity completes, it can pass its output to a subsequent activity. The most common dependency types are, on success. The next activity runs only if the preceding activity completes successfully. The most common path. On failure, the next activity runs only if the preceding activity fails. Ideal for error handling and notifications. On completion, the next activity runs regardless of whether the preceding activity succeeded or failed. On skip, the next activity runs if the preceding activity was skipped, e.g., due to an if condition, evaluating false. These dependencies allow you to build robust workflows with error handling, branching logic, and complex sequences of operations. Pipeline runs and monitoring. Every time a pipeline is triggered manually, on a schedule, or by an event, it creates a pipeline run. Each run has a unique ID, starts at a specific time, and can be monitored in the ADF Studio. You can see the status of each activity within the run: succeeded, failed, skipped, in progress, view individual activity logs, and troubleshoot any issues. 3.4 Bringing it together. The sales data example revisited. Let's quickly re-anchor our understanding with the sales data example from the previous chapter, now explicitly mapping it to our detailed building blocks. Scenario: copy daily sales data files, CSV, from Azure Blob Storage into a sales table in an Azure SQL database. Step 1. The connections, linked services. You create a linked service for your Azure Blob Storage account, ls Azure Blob Storage. This holds the connection string and authentication method to your storage. You create a linked service for your Azure SQL database, ls Azure SQLDB. This holds the connection string, server name, database name, and credentials to your database. Step 2. The data definitions, datasets. You create an input dataset, DS Daily Sales CSV, that uses ls Azure Blob Storage. This dataset specifies the container and folder path where your sales CSV files reside, e.g., raw data/sales/, and indicates that they are in CSV format. You create an output dataset, DS Sales Table SQL, that uses ls Azure SQLDB. This dataset specifies the target table within your database, e.g., DBO sales, where the data should be loaded. Step 3. The assembly line pipeline. You create a pipeline, pipeload daily sales. Inside this pipeline, you drag and drop a copy activity. You configure the copy activity. Its source is DS Daily Sales CSV. Its sync destination is DS Sales Table SQL. You might add an onSuccess dependency to another activity, like a delete activity to archive the processed CSV file, or a web activity to send an email notification, or an onFailure dependency to trigger an alert. Step 4. The trigger automation. You create an event-based trigger that monitors the raw data/sales/folder in your Azure Blob Storage. When a new file is created, this trigger fires. This trigger then starts a pipeline run for pipeload daily sales. During the pipeline run, the copy activity, utilizing the defined linked services and datasets, instructs the appropriate integration runtime to connect to Azure Blob Storage, read the incoming sales CSV, and efficiently write that data into the specified sales table in your Azure SQL database. This layered approach, starting from secure connections, defining specific data locations and formats, and finally building orchestrated workflows, makes Azure Data Factory a powerful and flexible tool for managing your data assets. With these core building blocks understood, we are now ready to explore how to actually move data with the copy activity and then transform it using other activities. Chapter 4. Moving data. The copy activity and beyond. The journey of data from its source to actionable insight almost always begins with movement. Raw data rarely originates exactly where it needs to be processed or analyzed. It might be born in an operational database, a third-party SaaS application, or a file dropped onto a network share. The first critical step in any data integration pipeline is to reliably and efficiently bring that data into a staging area or directly into its target destination. In Azure Data Factory, the undisputed workhorse for this crucial task is the copy activity. 4.1 The workhorse. The copy activity explained. The copy activity is undoubtedly one of the most frequently used activities in Azure Data Factory, and for good reason. Its primary function is straightforward: to copy data from a source data store to a sync destination data store. What makes it incredibly powerful and versatile is its ability to connect to a vast array of data sources and destinations. From relational databases like SQL Server, Oracle, and PostgreSQL, to various cloud storage services, Azure Blob Storage, Data Lake Storage, AWS S3, Google Cloud Storage, file systems, SFTP, HDFS, NoSQL databases, Cosmos DB, MongoDB, and even SaaS applications. Salesforce, Dynamics 365. Handle diverse data formats. It can intelligently read and write data in common formats such as CSV, JSON, Parquet, Avro, Orc, XML, or even simply as binary files. Perform type conversion. As data moves between different systems, the copy activity can automatically handle schema mapping and data type conversions, attempting to find the most appropriate corresponding type in the destination. Scale massively. Leveraging the underlying integration runtimes, the copy activity can process petabytes of data, scaling its computational resources dynamically. At its core, the copy activity links an input dataset, the source of your data, with an output dataset, the destination for your data. As discussed in Chapter 3, these datasets point to specific locations within the data stores defined by their respective linked services. 4.2. Configuring the copy activity. Source and sink. When you add a copy activity to your pipeline in ADF, you configure two main parts, the source and the sink. Source configuration. This section defines where the data comes from and how it should be read. Source dataset. You select one of the datasets you've already created, which defines the connection and basic structure of your input data. Querying data. Depending on the source type, you have options to filter or select specific data. For relational databases, you can provide a SQL query, e.g., select from orders where order date equals 2023 to 1:1, or simply specify a table view name. Using a query allows you to filter rows or columns before data is even copied, reducing the volume of data transferred. For file-based sources, you can specify a folder path, a file path, or even use wildcards, e.g., CSV to pick up all CSV files in a folder. You can also specify a list of files. This is very useful for scenarios where data arrives in multiple files. Partitioning data. For very large datasets, especially those in data lakes, you can configure partitioning to read data in parallel based on column values or file structure, significantly boosting performance. Change data capture, watermarking. A common pattern for incremental data loading is to use a watermark column, e.g., a timestamp or an auto-incrementing ID in your source. Each time the pipeline runs, it reads data only where the watermark value is greater than the last recorded value from the previous run. The copy activity doesn't inherently manage the watermark value itself, but ADF pipelines can use lookup activities and variables to store and retrieve these watermarks to make the copy activity execute incrementally. Sink destination configuration. This section defines where the data goes and how it should be written. Sink dataset. You select the dataset that defines the connection and structure of your output data. Write behavior. This is crucial and depends heavily on your target system. Insert. Simply append new rows to an existing table. Overwrite. Delete all existing data in the target table file and insert the new data. Use with caution. Upsert. Update existing rows if a match is found based on a key. Otherwise, insert new rows. This often requires additional configurations like specifying a staging area or using a dedicated upsert option for certain connectors, e.g., Azure Synapse Analytics. Append. For file-based syncs, this often means adding the new data to the end of an existing file. File naming conventions. When writing to file systems, you can define how output files are named. You can use dynamic content expressions to include timestamps, pipeline run IDs, or other variable values in the file name, which is vital for managing unique and traceable files, e.g., sales data timestamp parquet. Pre-copy script. For database syncs, you can often define a query to execute before the copy operation, such as truncating a table or disabling indexes for faster loads. 4.3 Column mapping. Ensuring data integrity. When data moves from one system to another, its schema, column names, and data types might change. The copy activity handles this through column mapping. Automatic mapping. If your source and sink schemas are identical or very similar, e.g., same column names and compatible data types, ADF can often automatically map columns for you. This is the simplest scenario. Manual mapping. You'll need to manually configure mappings when schema drift. Column names are different between source and sink, e.g., customer ID in source, cust ID in sink. Data type conversion. You need to explicitly convert a column from one data type to another, e.g., string to integer, date format conversion. Column exclusion. You only need to copy a subset of columns from the source. Derived columns. You want to apply a simple expression to transform a column, though for complex transformations, you'd move to data flows. The copy activity is quite smart about data type conversions. If you copy an integer column to a field defined as a string, it will usually handle the conversion gracefully. However, if the conversion is ambiguous or lossy, e.g., copying a text string that isn't a valid number into an integer field, you might encounter errors. Careful schema mapping and understanding your data types are crucial for successful copy operations. 4.4 Performance and Optimization. For enterprise-grade data pipelines, raw copying speed is paramount. ADF offers several features and considerations to optimize copy activity performance. Integration runtime, IR. The choice and configuration of your IR directly impacts performance. Azure IR. Fully managed, automatically scales. Its performance is often governed by Data Integration Units, DIUs. Self-hosted IR. Performance depends on the machine where it's installed, CPU, memory, network bandwidth. Ensure it's adequately sized. You can also scale out self-hosted IRs by installing multiple nodes pointing to the same logical IR, allowing them to share the workload. Data Integration Units, DIUs. For the Azure Integration Runtime, DIUs represent the compute power allocated for the copy activity. You can manually adjust the number of DIUs to increase or decrease the parallelism and throughput. More DIUs generally mean faster copy, but also higher cost. Parallel copies. The copy activity allows you to specify the number of parallel connections or threads it uses to copy data. Increasing this can utilize more bandwidth and speed up the copy, especially for large files or many small files. Staging for cloud data stores. For certain source and sync combinations, e.g., copying data from SFTP to Azure SQL, or from a third-party cloud service to Azure SQL. It can be faster to first copy the data to an intermediate staging area in Azure Blob Storage or Azure Data Lake Storage, and then copy from there to the final destination. This leverages Azure's internal high-speed network for the second leg of the journey and often allows for more efficient bulk insert methods. Data consistency and partitioning. When moving large volumes of files, particularly from a data lake, ensuring that the source data is partitioned logically, e.g., by date, can allow the copy activity to better utilize parallelism and improve performance. Monitoring copy activity. ADF provides detailed monitoring for each copy activity run, including data read written, total volume of data processed. Throughput. The speed of the copy, e.g., MBS or GBS. DIU consumption, how many DIUs were utilized. Durations, time taken for each stage of the copy. Analyzing these metrics helps identify bottlenecks and fine-tune configurations. 4.5 Common scenarios for the copy activity. The copy activity is incredibly versatile and forms the backbone of countless data pipelines. Cloud-to-cloud data migration. Migrating terabytes of data from an on-premises SQL Server database using self-hosted IR to Azure SQL Database or Azure Synapse Analytics. Data lake ingestion. Landing raw log files, sensor data, or bulk exports into Azure Data Lake Storage for later processing. Data synchronization. Regularly moving updated customer data from a CRM system, e.g., Salesforce, into an Azure-based analytical database for reporting. Archiving, moving old, less frequently accessed data from a high-cost database to cheaper Azure Blob Storage for long-term retention. Data replication, creating exact copies of files or folders from one storage account to another, possibly in a different region for disaster recovery. Bridging cloud and on-premises, connecting to legacy systems in your data center and moving their data securely to Azure services for modernization initiatives. 4.6 Beyond simple copy. Introduction to transformation. While the copy activity is powerful for moving data, its capabilities for transforming data are relatively basic. It can perform simple schema mapping, column renaming, and some direct data type conversions. However, if your data needs more complex operations like aggregating data across multiple rows, e.g., summing sales for each product, joining data from multiple sources based on complex conditions, pivoting or unpivoting data, applying sophisticated data cleansing rules, e.g., parsing unstructured text, standardizing addresses, implementing fuzzy matching or complex lookups. Then you'll need to look beyond the copy activity's direct capabilities. This leads us directly to the realm of data transformation and activities specifically designed for it, such as data flows, which we will explore in the next chapter. The copy activity, however, remains an indispensable tool. It's the foundational first step, ensuring that your raw materials are efficiently transported to the right location before any complex manufacturing transformation can begin. Mastering its configuration and optimization is key to building an efficient and cost-effective data factory. Chapter 5. Transforming data, data flows, and other activities. In the previous chapter, we mastered the art of data movement with the copy activity, the essential first step in any data journey. But moving data is only half the battle. Raw data, even when efficiently transported, is rarely in a state ready for direct analysis or consumption. It's often messy, inconsistent, incomplete, or simply not structured in a way that provides immediate insights. This is where data transformation comes in, the process of cleaning, reshaping, enriching, and validating data to make it fit for purpose. Imagine a block of marble. The copy activity might move that marble from the quarry to the sculptor's studio. However, it's the transformation process, the chiseling, sanding, and polishing, that turns the raw stone into a work of art. In Azure Data Factory, this transformative power is primarily wielded by data flows, alongside other specialized activities. 5.1 Data flows, visual, code-free transformation at scale. For years, complex data transformations required either extensive SQL scripting, custom code, like Python or Java with big data frameworks, or specialized, often expensive, on-premises ETL tools. Azure Data Factory's data flows revolutionize this by offering a completely visual, no-code, low-code environment for designing and executing sophisticated data transformations at cloud scale. What are data flows? At their core, data flows are graphical representations of your data transformation logic. You build them by dragging and dropping transformation nodes onto a canvas and connecting them in a logical sequence. Behind the scenes, ADF takes your visual design and translates it into executable code, specifically Spark jobs that runs on a managed Azure Databricks or Azure Synapse Spark cluster. This means no code required. You don't need to write a single line of Spark, Scala, Python, or SQL code to perform intricate data manipulations. Visual intuition. The drag-and-drop interface makes complex logic easier to design, understand, and debug. You literally see how your data is flowing and changing at each step. Managed compute. You don't need to provision, manage, or tune Spark clusters. ADF handles all the cluster management, scaling, and performance optimization for you. You simply specify the compute size you need, and ADF spins up the necessary resources, processes your data, and then tears them down, ensuring cost efficiency. Schema drift handling. Data rarely stays static. New columns might appear, existing ones might change data types. Data flows are designed to gracefully handle schema drift, allowing for flexible pipelines that adapt to evolving data structures without constant manual updates. Big data ready? Because they leverage Spark, data flows are inherently designed for large-scale data processing, handling petabytes of data with ease across distributed computing environments. Building a data flow. Common transformations. A data flow typically starts with one or more source transformations and ends with one or more sink transformations. In between, you orchestrate a series of intermediate transformations. Source transformation. This is where your raw data enters the data flow. You define which dataset, referencing a linked service, acts as the input. You can have multiple sources in a single data flow, allowing you to combine data from different origins. Sink transformation. This is where the transformed data exits the data flow and is written to its final destination, another dataset. You can write the output to various data stores and even specify different write methods like insert, update, or upsert. Between the source and sink, you use a rich library of transformations. Select. Similar to Select in SQL, this allows you to choose which columns to keep, rename columns, or reorder them. You can easily remove sensitive or unnecessary columns. Derived column. This transformation allows you to add new columns to your data stream or change the values of existing columns. You can use powerful expressions, similar to Excel formulas or simple programming functions, to concatenate strings, perform mathematical calculations, extract substrings, or apply conditional logic. For example, creating a full name column by combining first name and last name or calculating sales tax on an amount column. Filter. Analogous to the where clause in SQL, this allows you to filter rows based on conditions. For example, keeping only sales records from a specific region or customers above a certain age. Aggregate. This is for summarization. You can group data by one or more columns and then apply aggregate functions like sum, AVG, count, min, max. For example, calculate total sales per product category or average customer rating per month. Join. Combine data from two or more incoming streams based on common key columns, similar to SQL joins, inner, left outer, right outer, full outer, cross. For example, joining customer data with order data. Lookup. For situations where you need to look up a value from a smaller dataset based on a key from your main stream. Unlike a join, a lookup only adds columns from the lookup stream if a match is found. It doesn't filter rows from the primary stream. Useful for enriching data with reference information, e.g., looking up product names from a product ID. Union. Combine rows from two or more streams with compatible schemas, similar to union all in SQL. Conditional split. Divide your data stream into multiple streams based on conditions. For example, routing high priority orders to one path for immediate processing and low priority orders to another. Exists. Checks if rows from one stream exist or don't exist in another stream, useful for data validation or filtering. Sort. Orders rows based on specified columns, useful for presentation or for operations that require sorted input. Window. Perform calculations over a defined window of rows, such as calculating rolling averages, ranks, or lead lag values, similar to SQL window functions. Surrogate key automatically generates a unique sequential integer key for each row in your data stream, essential for creating dimension tables in data warehousing. Row modifier, upsert, update, delete, insert. This powerful transformation allows you to define how rows are written to the sink, enabling operations beyond simple inserts, such as updating existing records or deleting records based on conditions. This is critical for maintaining slowly changing dimensions or synchronizing data. Executing data flows. Once designed, a data flow is executed within an ADF pipeline by using a data flow activity. You simply drag the data flow activity onto your pipeline canvas and select the data flow you want to run. When the pipeline executes, the data flow activity spins up the dedicated Spark cluster, runs your transformations, and writes the output. 5.2 Other transformation activities. When to choose what. While data flows handle many transformation needs visually, ADF provides other activities for specific scenarios, especially when you need to leverage existing code or integrate with other Azure services. Stored procedure activity. When to use. If your transformations are primarily done within a relational database and you have existing stored procedures that perform complex data manipulations, this activity is perfect. It simply executes a stored procedure on a connected database, defined by a linked service. Benefits. Leverages database native capabilities and existing investments, often very performant for database-specific operations. Considerations. Tightly couples your ETL to the database backend. May not scale as well for transformations across diverse, non-database data sources, e.g., files or APIs. Azure Databricks Notebook activity. When to use. For highly complex transformations, advanced analytics, machine learning model training, or when you prefer to write code in Python, Scala, R, or SQL using the Spark framework. ADF can trigger a Databricks notebook that performs the transformation logic. Benefits. Unparalleled flexibility and power, integration with open-source libraries, ideal for data science workloads. You have full control over the Spark cluster configuration within Databricks. Considerations: requires coding skills in Spark-supported languages. You manage the Databricks workspace and cluster, which adds some operational overhead compared to fully managed data flows. Azure Function Activity. When to use: to execute small, serverless pieces of custom code, e.g., Python, C#, Node.js, for specific, lightweight transformations that aren't well suited for data flows or stored procedures. Think of tasks like calling a third-party API for data enrichment, performing custom data validation, or triggering external processes. Benefits: highly cost-effective for intermittent, short-running tasks. Extremely flexible for custom logic. Considerations: not designed for large-scale data transformations, better for row-level or small-batch processing. HD Insight Activities, Hive, Pig, Spark, MapReduce. When to use: if you have existing investments or expertise in traditional Hadoop ecosystem technologies, Hive queries, Pig scripts, Spark applications, MapReduce jobs, and want to run them on a managed Hadoop cluster in Azure. Benefits: leverages existing code bases and skills. Considerations: less commonly used for new transformations compared to data flows or Databricks, as HD Insight clusters can be more complex to manage and provision for ad hoc ETL, primarily for lift and shift of legacy Hadoop workloads. 5.3 Choosing your transformation strategy. The choice of transformation activity depends on your specific needs, team skills, data volume, and performance requirements. For most large-scale, enterprise-grade data transformations, data flows are often the first choice due to their visual nature, managed Spark backend, and comprehensive transformation library. They are ideal for building robust, scalable ETL/ELT pipelines without writing code. For database-centric transformations or leveraging existing SQL logic, stored procedure activity is a strong contender. For highly specialized or custom code-driven transformations, machine learning, or complex data science workflows, Azure Databricks Notebook Activity provides the most power and flexibility. For lightweight, event-driven, or external API interactions, Azure Function Activity offers a serverless, cost-effective solution. Often, a single pipeline might combine multiple transformation approaches. For example, a pipeline could use a copy activity to land raw data in Azure Data Lake, then a data flow activity to clean and reshape the data, followed by a stored procedure activity to load the final, transformed data into a data warehouse, and finally an Azure Function activity to trigger a reporting dashboard update. ADF's strength lies in its ability to orchestrate these diverse activities seamlessly. Understanding the strengths and weaknesses of each transformation tool within Azure Data Factory empowers you to select the most appropriate method for your specific data challenges, paving the way for efficient, scalable, and insightful data solutions. Chapter 6: Orchestration and Control, Making Pipelines Intelligent. In the earlier chapters, we learned about the fundamental building blocks of Azure Data Factory: linked services for connections, datasets for data definitions, and activities for performing specific tasks like copying or transforming data. We also started to build pipelines as a sequence of these activities. However, a truly robust and intelligent data factory doesn't just run linear sequences of tasks. It needs to make decisions, adapt to changing conditions, handle errors gracefully, and process data dynamically. This is the essence of pipeline orchestration and control. Think of orchestrating a symphony. It's not just about each musician playing their part. It involves a conductor who directs the flow, ensures instruments play at the right time, adjusts volume based on cues, and handles any unexpected interruptions. Similarly, Azure Data Factory pipelines can be designed to act as intelligent conductors for your data. 6.1 Control Flow Activities, the Logic Builders. Control flow activities are the glue that allows you to specify the execution order, group activities, and define the conditional logic of your pipeline. They don't move or transform data themselves. Rather, they direct the flow of operations based on outcomes or defined conditions. Here are some of the most commonly used control flow activities. If condition activity. This is your primary decision-making tool, akin to an if-then-else statement in programming. It evaluates a Boolean expression, a true-false statement, and executes a different set of activities based on the outcome. For example, if a file exists, then process it, otherwise send an alert. Or, if the row count from a previous activity is greater than 0, then proceed with the load. This allows you to build branching logic into your pipelines. For each activity, data often comes in batches, many files, multiple tables, or a list of items to process. The for each activity lets you iterate over a collection, an array of items, and execute a defined set of activities for each item in that collection. This is incredibly powerful for scenarios like processing every new file that lands in a specific folder, loading data from multiple tables in a database, applying the same transformation logic to different regional datasets. Crucially, for each activities can often be configured to run iterations in parallel, significantly speeding up processing for large collections. Switch activity. While you can use nested if conditions for multiple choices, a switch activity provides a cleaner, more organized way to handle multiple mutually exclusive conditions. It evaluates an expression and executes a different set of activities based on the output matching predefined cases. For example, if a data source type, a pipeline parameter, is SQL, execute SQL-specific activities. If it's blob, run file-related activities. Lookup activity. Though it retrieves data, the lookup activity is often utilized for control flow. It reads a small amount of data from a data source, e.g., a row from a configuration table, a file path, or the current watermark value from a database query, and outputs it as an array or a single row. This output can then be used by subsequent activities for decision-making. For instance, using lookup to retrieve a list of files to process, which then feeds into a for-each loop. Web activity. This is your Swiss Army knife for integrating with external services via HTTP/HTTPS. You can use it to call an external REST API, trigger an Azure function, which might send an email or an SMS, or even post messages to collaboration tools like Microsoft Teams or Slack. While it can also receive data, its strength in orchestration lies in initiating external actions based on pipeline events, e.g., sending a successful completion notification. Wait activity. Sometimes, your pipeline needs to pause for a fixed duration before proceeding. Perhaps an external system needs time to prepare data, or you want to introduce a delay between calls to an API to avoid hitting rate limits. The wait activity simply pauses the pipeline for a specified time. Validation activity. This activity allows you to check for the existence of a file, folder, or table, and optionally verify that it contains data. If the validation condition is not met, the activity can be configured to fail the pipeline or trigger downstream conditional logic. It's useful for ensuring prerequisites are met before proceeding with costly operations. Set variable/append variable activity. These activities allow you to define and manipulate variables within your pipeline run. You can set a variable's value or append a value to an array variable. Variables are temporary storage that live only for the duration of the pipeline run and are frequently used to pass information between activities, store intermediate results, or build dynamic expressions. Execute pipeline activity. This is crucial for building modular and reusable solutions. It allows one pipeline to call another pipeline a child pipeline. This promotes good design principles, allowing you to break down complex workflows into smaller, manageable, and independently testable units. For example, a master orchestration pipeline could call several data ingestion pipelines for different data sources. 6.2 Making pipelines dynamic, parameters and variables. To make your pipelines adaptable and reusable, you need to introduce dynamism. ADF offers two primary mechanisms: pipeline parameters, what they are, values that you pass into a pipeline when it is triggered. Purpose, to make a pipeline generic so it can be used in various scenarios without modification. For example, a pipeline designed to load sales data could accept a region name parameter, allowing the same pipeline to load data for North, South, East, or West regions by simply changing the parameter value at runtime. How they work: you define parameters at the pipeline level, giving them a name, data type, string, integer, Boolean, array, object, and optionally a default value. Usage. Parameters are typically set by triggers or provided manually if you run the pipeline on demand. Inside the pipeline, activities can access these parameters using dynamic content expressions. For example, to use a region name parameter in a copy activity's source path, you might write it pipeline. Parameters region name. Variables. What they are. Values that exist and can be modified within a pipeline run. They are internal to the pipeline's execution. Purpose. To store temporary data, intermediate calculations, or status flags that evolve as the pipeline executes. For example, accumulating a list of successfully processed files, holding a dynamically computed file path, or tracking a row count. How they work. You initialize variables at the pipeline level. During the pipeline run, set variable or append variable activities can update their values. Usage. Variables are accessed using dynamic content similarly to parameters. At variables, my variable name. System variables. ADF also provides built-in system variables that give you access to information about the current pipeline run, trigger, and more. Examples include, at pipeline, run ID, a unique identifier for the current pipeline run. At pipeline, trigger time, the timestamp when the pipeline was triggered. At activity, activity name .output.property allows you to reference the specific output of a preceding activity. This is extremely important, as it's how you pass data between sequential activities, e.g., getting the row count from a lookup activity or the name of a file generated by an activity. Dynamics in action, mini case study. Incremental data load. Let's consider an intelligent pipeline for an incremental data load. You want to load only new or updated customer records from a database. Lookup activity. First, use a lookup activity to query your data warehouse for the last loaded timestamp, your watermark. Set variable activity. Store this last loaded timestamp in a pipeline variable. Copy activity. Configure your copy activity to copy data from the source database, where last modified date at variables, last loaded timestamp. Another set variable activity. After a successful copy, update the last loaded timestamp variable with the current maximum last modified date from the newly loaded data. Stored procedure activity. Finally, execute a stored procedure in your data warehouse that updates the last loaded timestamp in your watermark table with the value from your variable. This ensures that each subsequent run only fetches new data, making the pipeline efficient and intelligent. 6.3 Error handling and robustness. A key aspect of intelligent orchestration is the ability to gracefully handle failures. When something goes wrong in a data pipeline, you don't want it to just stop silently. You need to be informed, and ideally, the pipeline should attempt to recover or take corrective action. Dependency chains for error paths. In Chapter 3, we briefly mentioned activity dependencies on success, on failure, on completion, on skipped. These are fundamental to building robust error handling. You design a happy path using on-success dependencies. For error handling, you add an activity, e.g., a web activity to send a notification, or an execute pipeline activity to trigger a cleanup routine, and link it from the problematic activity using an on-failure dependency. This means the error handling activity will only execute if the preceding activity fails. On completion is useful if you want an activity to always run, regardless of success or failure, e.g., a logging or cleanup step. Simulating try-catch blocks. While ADF doesn't have explicit try-catch blocks like some programming languages, you can simulate this. Wrap a group of activities that might fail within a dedicated try branch. If any activity in that branch fails, redirect the flow via an on-failure dependency to a catch branch, where you execute error handling activities. Notifications and alerts. Informing stakeholders about failures is critical. Common methods include web activity, call an Azure function that sends an email, or directly post to a webhook for Teams Slack. Azure Monitor alerts. Configure alerts based on ADF pipeline run metrics, e.g., a failed run to trigger email, SMS, or webhook notifications. Logging and monitoring. ADF provides extensive built-in logging for every pipeline run and activity. This is invaluable for troubleshooting. You can see the input and output of each activity error messages, and duration. A well-designed pipeline will also include details and activity outputs, e.g., row counts, file names processed, that can aid in diagnostics. 6.4. Building modular and reusable pipelines. Just like software development encourages reusable functions and modules, data engineering benefits from modular pipeline design. The execute pipeline activity is your primary tool for this. Advantages of child pipelines. Reusability. Create a general-purpose child pipeline, e.g., for logging or for a specific data source ingestion, and call it from multiple parent pipelines. Maintainability. Changes to a common process only need to be made in one child pipeline definition. Testability. Smaller, focused child pipelines are easier to test independently. Clarity. Complex orchestrations become easier to understand when broken down into logical subpipelines. Error handling. You can centralize error handling logic in a child pipeline that is called on failure. When calling a child pipeline, you can pass parameters to it, just as you would to a function in programming. This allows the child pipeline to act dynamically based on the parameters it receives from the parent. By leveraging control flow activities, parameters, variables, robust error handling, and modular design, you transform your data factory from a simple task runner into an intelligent, adaptive, and resilient system that can confidently manage the complexities of your data landscape. In the next chapter, we'll explore how these intelligent pipelines are put into motion and monitored through scheduling, monitoring, and alerting. Chapter 7. Scheduling, Monitoring, and Alerting. Keeping your factory running smoothly. Building robust data pipelines is a significant achievement, but the true value of an automated data factory comes not just from what it can do, but from when it does it and how effectively you can oversee its operations. A factory that only produces goods when someone manually flips a switch, or one that breaks down without anyone noticing, is inherently inefficient and unreliable. In Azure Data Factory, the concepts of scheduling, monitoring, and alerting are paramount. They ensure your data pipelines run precisely when needed, provide visibility into their performance and health, and proactively notify you of any issues, allowing your data factory to operate smoothly and reliably, turning raw data into valuable insights around the clock. 7.1. Orchestrating time. Scheduling your pipelines with triggers. Pipelines are designed to automate tasks, but automation requires a mechanism to kick them off. This is where triggers come into play. A trigger is a processing unit that determines when a pipeline execution should be started. ADF offers several types of triggers to cater to different scheduling needs. Schedule trigger, the regular roster. What it does: the most common type, a schedule trigger runs a pipeline at specified recurrent intervals. Think of it as setting a recurring meeting on a calendar. Use cases: ideal for daily, hourly, weekly, or monthly data loads, batch processing, or reporting jobs. For example, copying a full dump of customer data every Sunday morning or consolidating sales figures every night. Configuration: you define a start date, a recurrence pattern, e.g., every 1 hour, every 24 hours, and optionally specific times of the day or days of the week. You can also specify the time zone, ensuring your pipeline runs correctly regardless of where your users or data sources are located. Dynamic inputs. Schedule triggers can pass parameters to the pipeline, allowing for subtle variations in each run. For example, a daily pipeline might receive a run date parameter with the current date, enabling it to process only that day's specific data. Tumbling window trigger, the time-sliced manager. What it does: a tumbling window trigger fires at a regular, fixed-size time interval, but unlike a simple schedule trigger, each interval window is distinct and doesn't overlap. It's particularly useful for historical data processing or scenarios where you need to process data in consecutive, non-overlapping chunks. Use cases: processing hourly sales data from the past month, where each run corresponds to a specific hour, incrementally loading data where each batch precisely covers a time slot with no gaps or overlaps. Key features: fixed size, you define the duration of each window, e.g., 1 hour, 24 hours. Start and end times. Each triggered pipeline run receives a window start and window end parameter, which are the exact boundaries of the data window it should process. This is crucial for precise data partitioning. Self-dependency, optional. A powerful feature where one Windows run depends on the successful completion of a previous Windows run. For example, if you're processing daily data, the processing for January 2nd won't start until January 1st's processing is successfully finished. This is vital for maintaining data integrity and ensuring chronological order of processing. Analogy: imagine a factory that produces a report at the end of every production shift. A tumbling window trigger ensures that each report covers exactly one shift, e.g., 8 a.m. 4 p.m., 4 p.m. 12 a.m., 12 a.m. 8 a.m., and the next shift's report won't start until the previous one is fully generated. Event-based trigger, the reactive listener. What it does: this trigger responds instantaneously to specific events happening in your Azure environment, primarily related to data landing in Azure storage accounts. It allows your data factory to be event-driven, reacting to changes rather than just running on a schedule. Use cases: ingesting new files into a data lake immediately upon arrival, triggering a data processing pipeline when an external application drops a new report, archiving files as soon as they are deleted from a hot storage tier. Configuration: you specify the Azure storage account, the containers, and the type of event, e.g., blob created, blob deleted. You can also apply filters based on blob names, e.g., CSV in a specific folder. Benefit: reduces latency significantly. Instead of waiting for a scheduled job to run, data processing begins as soon as the relevant event occurs. This is vital for near real-time analytical systems. Stopping triggers: you can start and stop triggers without affecting the pipeline definition. This is useful for maintenance, deploying updates, or pausing operations. 7.2 Keeping an eye on things. Monitoring your pipelines. Once your pipelines are created and scheduled, they operate behind the scenes. But what if something goes wrong? How do you know if your data made it to its destination or if a transformation failed? This is where robust monitoring tools become indispensable. Azure Data Factory provides a comprehensive monitoring experience within the Azure portal's ADF Studio. The Monitoring Hub. The Monitor tab in your ADF Studio acts as your central control room for operational insights. Here, you can view the status of all your pipeline runs and activity runs. Pipeline runs. This view provides a high-level overview of each time a pipeline was triggered and executed. You see the run ID, start time, end time, duration, and overall status: succeeded, failed, canceled, in progress. You can filter these runs by pipeline name, status, time range, and trigger type. Activity runs. For a deeper dive, you can click on a specific pipeline run to inspect its individual activity runs. This shows you each activity within that pipeline, its duration, and its status. If an activity fails, you can easily identify it. Gantt chart view. While not a visible image in this book, imagine a timeline where each horizontal bar represents a pipeline run or an activity run. This visual representation helps you quickly see the sequence and overlap of your runs, identify bottlenecks, and understand the flow of execution over time. Input, output, and errors. For each activity run, you can inspect the input and output JSON payloads. This is incredibly helpful for debugging, as it shows you exactly what data the activity received and what it produced, as well as any specific error messages if it failed. Key performance metrics. The monitoring view provides crucial metrics that help you assess the health and performance of your data factory. Duration. How long did the pipeline or activity take to complete? Spikes in duration can indicate performance issues or unexpected data volumes. Data read-written. For copy activities, this shows the volume of data processed. This helps you confirm data movement and understand the scale of operations. Throughput. The speed at which data was moved or processed, e.g., MBS or ROS. A drop in throughput often signals a bottleneck. Data Integration Unit, DIU consumption. For the Azure Integration Runtime, this shows the processing power consumed. Helpful for cost optimization and capacity planning. Success rate, failure rate. Track the percentage of successful runs over time to gauge overall pipeline reliability. Integration with Azure Monitor and Log Analytics. For advanced monitoring, centralized logging, and deeper analytics, ADF seamlessly integrates with Azure Monitor. Diagnostic settings. You can configure ADF to send its operational logs, pipeline runs, activity runs, trigger runs to Azure Log Analytics. Log Analytics Workspaces. This is a powerful analytics service where you can store, query, and analyze your logs using Kusto Query Language, KQL. You can build custom dashboards, identify trends, investigate historical performance, and analyze specific error patterns across all your ADF instances. Metrics. ADF also emits various metrics to Azure Monitor, such as successful runs, failed runs, pipelines queued, and more. These metrics can be visualized on custom dashboards in Azure Monitor. 7.3 Getting notified. Setting up alerts. Monitoring is reactive. You have to actively check the dashboard. Alerting is proactive. It brings critical information directly to you. An intelligent factory doesn't just display problems, it screams for help when something goes wrong. Azure Monitor alerts and action groups. The most robust way to set up alerts for ADF is through Azure Monitor. Alert rules. You define alert rules based on metrics or log data. For example, alert me if any pipeline run status is failed. Alert me if the number of queued pipeline runs exceeds 10 for more than 5 minutes. Alert me if a specific pipeline's duration exceeds 30 minutes. Conditions. You specify the threshold and aggregation period for the metric or log query that triggers the alert. Action groups. Once an alert is triggered, an action group defines who gets notified and how. An action group can send email notifications to individuals or distribution lists, send SMS messages, trigger a webhook, e.g., to post a message in Microsoft Teams or Slack, call an Azure function for custom notification logic, like formatting a detailed email or integrating with an IT service management system. Initiate an Azure Logic app for more complex automated responses. In pipeline, alerting with web activities. As we discussed in Chapter 6, you can also build specific notification steps directly into your pipelines using web activities in conjunction with conditional logic on failure dependencies. Scenario: if a critical copy activity fails, an activity linked on failure can execute a web activity that calls an Azure function. This Azure function then sends a richly formatted email or a specific alert to your team, perhaps including details from the failed activity's output. Benefit: allows for highly customized notifications tailored to the specific failure point within a pipeline, providing more context than a generic Azure Monitor alert. By combining scheduled triggers, detailed monitoring via the ADF Studio and Log Analytics, and proactive alerts through Azure Monitor, you ensure that your data factory is running optimally. Problems are detected and addressed quickly, and your data flows smoothly and reliably from source to insight. This operational excellence is the hallmark of a mature data integration strategy. Chapter 8: Security and Governance, Protecting Your Data Pipelines. In the world of data, insights are gold, but data itself is a prized asset demanding stringent protection. As organizations increasingly rely on data for critical operations and strategic decisions, ensuring its security and maintaining proper governance over its lifecycle becomes paramount. Moving data into and across cloud environments, while offering immense flexibility and scalability, also introduces new considerations for how that data is safeguarded. Azure Data Factory, as your central data integration hub, handles vast amounts of potentially sensitive information. Therefore, understanding and implementing its security features and adhering to sound governance practices are not optional. They are fundamental requirements for building a reliable and compliant data factory. 8.1 The imperative of data security in the cloud age. Data breaches can be catastrophic, leading to financial losses, regulatory fines, reputational damage, and loss of customer trust. Beyond just protecting against malicious attacks, robust security ensures confidentiality, preventing unauthorized access to sensitive data. Integrity, ensuring data remains accurate and complete, preventing tampering. Availability, guaranteeing authorized users and systems can access data when needed. Furthermore, a growing myriad of global regulations, like GDPR in Europe, HIPAA for healthcare data in the US, and various local data residency laws impose strict requirements on how personal and sensitive data is handled. Compliance often hinges on implementing strong security controls. When you move to the cloud, the responsibility for security operates under a shared responsibility model. Microsoft is responsible for the security of the cloud, the underlying infrastructure, hardware, and network, while you are responsible for security in the cloud, your data, pipelines, network configurations, and access controls. Azure Data Factory provides the tools. It's up to you to use them effectively. 8.2 Azure Security Foundation for ADF. ADF leverages fundamental Azure security services to provide a robust framework. Azure Active Directory, Azure AD, Identity and Access Management. Azure AD is Microsoft's cloud-based identity and access management service. It's the cornerstone of security for almost all Azure services, including ADF. Centralized user and group management. You manage who can access your data factory and what they can do within it. Users and groups are defined in Azure AD. Role-based access control, RBAC. RBAC allows you to assign specific permissions to users, groups, or managed identities for Azure resources at different scopes, e.g., subscription, resource group, or individual data factory. For ADF, common built-in roles include Data Factory Contributor, can create and manage all data factory resources, pipelines, datasets, linked services, etc. Data Factory Operator, can view data factory resources and monitor pipeline runs, but cannot create or modify them. Ideal for operational teams. Reader, can view all data factory resources. Principle of least privilege. A core security tenet is to grant users and applications only the minimum permissions necessary to perform their tasks. RBAC helps enforce this. Azure Key Vault, secure credential management, handling sensitive credentials, passwords, API keys, connection strings, directly within your data factory definitions is generally considered a bad practice. This is where Azure Key Vault comes in. Centralized secure storage. Key Vault provides a secure, centralized store for secrets, encryption keys, and certificates. Referencing secrets. Instead of directly embedding a password in an ADF linked service, you can configure the linked service to reference a secret stored in Key Vault. ADF retrieves the secret at runtime. Benefits. Reduces the risk of accidental exposure, e.g., in source control, allows for auditing of secret access, and simplifies secret rotation. You change the secret in Key Vault, and ADF automatically picks up the new value without needing a pipeline redeployment. Managed Identities for Azure Resources, MIs, passwordless authentication. Managed identities are a feature of Azure AD that provide Azure services, like Data Factory, with an automatically managed identity that can authenticate to other Azure services securely, without developers needing to manage credentials. System-assigned MI, an identity tied directly to a specific Azure resource, e.g., your data factory. Its lifecycle is tied to the resource. User-assigned MI, an identity that you create and manage independently. It can be assigned to multiple Azure resources. How ADF uses them. Your data factory's managed identity can be granted permissions via RBAC to access other Azure resources like Azure Storage Accounts, Azure SQL databases, or Azure Synapse Analytics workspaces. Then, your ADF linked services for these resources can be configured to use the data factory's managed identity for authentication, eliminating the need to store any passwords or access keys in the linked service itself. Benefits: highly secure, simplifies credential management, and eliminates the need for manual secret rotation. This is the recommended approach for Azure to Azure service communication. 8.3 Securing data movement and access within ADF. Beyond identity, securing the physical movement and processing of data is critical. Network security. How data travels between ADF and your sources syncs. Private endpoints. For Azure Data Services, Storage, SQL DB, Synapse, private endpoints allow you to establish a secure, private connection from your Azure Virtual Network, VNet, to the service over Microsoft's backbone network, bypassing the public internet. ADF can use these private endpoints, meaning your data pipelines can connect to these services privately. This significantly reduces the attack surface and enhances compliance. Managed Virtual Network, VNet, in ADF. Azure Data Factory offers a powerful feature called Managed Virtual Network. When enabled, ADF creates a dedicated, isolated VNet where its compute resources, like the Spark clusters for data flows or the managed integration runtime for private endpoints, run. This VNet is fully managed by Microsoft, but you can create managed private endpoints within it to connect privately to your Azure data stores or even self-hosted IRs in your own VNet. This provides an additional layer of network isolation for your data processing. Self-hosted integration runtime, SHIR, and network access. For connecting to on-premises data sources behind your corporate firewall or IA SVMS in your own VNet, the self-hosted integration runtime is used. The SHIR acts as a secure proxy. Crucially, the SHIR initiates outbound connections over HTTPS to ADF. This means you only need to open outbound port 443 on your corporate firewall. No inbound ports are required, greatly simplifying network configuration and enhancing security. Encryption, protecting data while it's stored and while it's in transit. Data at rest. ADF itself is an orchestration service and does not store your actual data permanently. However, the data stores it reads from and writes to, e.g., Azure Storage, Azure SQL Database, inherently offer data at rest encryption. Azure Storage accounts encrypt data by default using Microsoft-managed keys, with customer-managed keys, CMK, as an option for enhanced control. Data in transit. All communication within Azure Data Factory and between ADF and other Azure services, and between SHIR and ADF, is encrypted using industry-standard protocols like TLS, Transport Layer Security, over HTTPS. Data flow security. Azure data flows execute on fully managed Spark clusters within ADF's environment. When managed VNet is enabled for your ADF, these Spark clusters also run within that isolated network, allowing them to process data from sources and write to sinks using managed private endpoints, ensuring that your transformation logic executes in a secure, private context. 8.4 Governance, ensuring order and compliance. Security focuses on protection. Governance focuses on the overarching policies, processes, and tools that ensure data is managed effectively, consistently, and compliantly throughout its lifecycle. Naming conventions. Establishing clear, consistent naming conventions for all your ADF resources, pipelines, datasets, linked services, activities is fundamental to good governance. Benefits. Improves readability, discoverability, and maintainability. Makes it easier for new team members to understand existing solutions. Essential for large-scale deployments and automation, e.g., using scripts that rely on predictable names. Example, LS Azure SQL DB Finance, DSCSV Sales Data, Pipe Extract Transform Load Customers. Environment Management. Development, test, production, dev/test/prod. Best practice dictates having separate ADF instances for each environment. This ensures that changes are developed and thoroughly tested in isolated environments before being promoted to production, preventing accidental disruption of live data flows. CI/CD, continuous integration, continuous deployment. Automating the deployment of ADF artifacts, pipelines, etc. between environments is a key governance practice. Tools like Azure DevOps or GitHub Actions enable this, ensuring consistent, repeatable, and audited deployments. This topic will be explored further in a later chapter. Cost management. While ADF bills on a pay-as-you-go model, activity runs, DIU hours, data flow cluster hours, effective governance includes monitoring and optimizing costs. Understanding the pricing model. Know how each component of ADF contributes to your bill. Optimizing pipelines. Design pipelines for efficiency, e.g., incremental loads, efficient transformations, appropriate use of compute resources to avoid unnecessary costs. Alerting on spend. Use Azure Cost Management to set up budgets and alerts for your ADF instances to prevent unexpected expenses. Auditing and logging. Comprehensive logging provides an immutable record of what happened in your data factory. Azure Monitor Logs log analytics. As discussed in Chapter 7, configuring diagnostic settings to send ADF logs to log analytics is crucial. This allows you to track pipeline runs, who initiated a run, when it started ended, its success or failure. Monitor changes, audit data to see who created, modified, or deleted ADF resources. Compliance, provide evidence for regulatory audits. Troubleshooting, diagnose issues by reviewing historical activity. Data lineage, understanding the journey of data from its source system through various transformations in your data factory to its final destination, e.g., a report or dashboard. ADF's monitoring provides runtime lineage, what happened during a specific execution. For design time lineage, the overall data flow architecture. Tools like Azure Purview or careful documentation of your ADF solutions are invaluable for maintaining a clear understanding of your data landscape. By integrating these robust security features and adhering to sound governance practices, your Azure Data Factory becomes not just a powerful engine for data integration, but also a trustworthy guardian of your most valuable digital asset, your data. Chapter 9, Real-World Scenarios, Putting ADF to Work. Understanding the individual building blocks of Azure Data Factory is a great start, but the true power of ADF comes alive when you combine these components to solve real-world data challenges. In this chapter, we'll explore several common scenarios, illustrating how linked services, datasets, pipelines, activities, and triggers orchestrate seamless data movement and transformation for various business needs. These simplified case studies will provide practical context, demonstrating how the concepts we've discussed translate into functional data solutions. Scenario 1. Hybrid data ingestion from on-premises to Azure Data Lake. The problem: a long-standing retail company stores its daily point-of-sale (POS) transaction data in an on-premises SQL Server database. To leverage cloud analytics tools and machine learning, they need to ingest this data daily into an Azure Data Lake Storage Gen 2 account, specifically as Parquet files for optimal performance in big data queries. They also need to ensure only new transactions are copied each day to avoid reprocessing existing data. The solution outline. This scenario requires bridging the on-premises environment with Azure, necessitating a secure gateway. It also demands an incremental loading strategy. Hybrid connectivity, self-hosted integration runtime. Key component: a self-hosted integration runtime, SHIR, is installed on a dedicated virtual machine or server within the company's on-premises network. This SHIR will act as a secure communication bridge, allowing Azure Data Factory to connect to the internal SQL Server database without opening inbound firewall ports. It only requires outbound HTTPS access to Azure. Justification: the SHIR is essential for connecting to data sources that are not publicly accessible or reside behind corporate firewalls. Connections, linked services. On-premises SQL Server linked service. This will point to the internal SQL Server instance and use the installed self-hosted IR. It will contain connection details like the server name, database name, and authentication credentials, ideally stored in Azure Key Vault for security. Azure Data Lake Storage Gen 2 linked service. This will point to the target ADLS Gen 2 account in Azure. It will use the default Azure integration runtime as it's an Azure-to-Azure connection. Data definitions, datasets. Source dataset, on-premises POS data, configured to use the on-premises SQL linked service pointing to the POS transactions table. It defines the schema of the POS data. Sync dataset, ADLS Gen 2 Parquet, configured to use the ADLS Gen 2 linked service, pointing to a specific folder path, e.g., raw/post-transactions/ within the data lake. Its format is defined as Parquet and typically includes dynamic file naming based on the load date for better organization, e.g., post-transactions 2023-10 to 27 Parquet. The orchestration pipeline. Name: pipe ingest POS transactions daily. Parameters: it might accept a load date parameter, which the everyday trigger will provide. Activities: Lookup activity, get watermark. This activity reaches out to a control table, perhaps in a lightweight Azure SQL database or even a small JSON file in ADLS that stores the last loaded transaction ID. This ID represents the highest transaction ID successfully processed in the previous daily run. Copy activity. Source, the on-premises POS data dataset. Instead of selecting the whole table, the query for the source will use the last loaded transaction ID retrieved by the lookup activity to fetch only transactions where their ID is greater than the watermark. This ensures incremental loading. Sync, the ADLS Gen 2 Parquet dataset. The file name will be dynamically generated using the load date parameter. Stored procedure activity, update watermark. After the copy activity successfully completes, this activity will execute a stored procedure in the control database to update the last loaded transaction ID with the highest transaction ID from the data just copied. This ensures the next run starts from the correct point. Alternatively, a web activity could trigger an Azure function to update a file in ADLS. Error handling. An on-failure dependency from the copy activity could trigger an Azure function or web activity to send an email alert to the data engineering team. The automation trigger. Type, a schedule trigger. Configuration, set to run once every 24 hours, for example, daily at 3:00 a.m., to ensure minimal impact on the operational database during business hours. The trigger will also dynamically pass the current UTC date to the pipeline's load date parameter. Outcome. Every morning, the pipeline automatically wakes up, securely connects to the on-premises SQL server, extracts only the new POS transactions, converts them to Parquet format, and lands them in a dated folder within the Azure Data Lake. This provides a fresh, organized, and analyzable dataset for business intelligence and data science initiatives. Scenario 2. Data transformation in data lake and loading to data warehouse. The problem: the raw POS transaction data from Scenario 1 and raw product catalog data, also periodically landed in the data lake, need to be joined, cleansed, aggregated, and then loaded into a star schema data warehouse in Azure Synapse Analytics for executive reporting. Some transactions might have missing product IDs and should be flagged or diverted. The solution outline. This is a classic ELT, extract, load raw, transform, load into final target, pattern, heavily leveraging ADF's visual transformation capabilities. Connections, link services. Azure Data Lake Storage Gen 2 linked service points to the ADLS Gen 2 where raw POS and product data reside. Azure Synapse Analytics link service points to the Synapse workspace and the specific dedicated SQL pool, data warehouse. Data definitions, datasets. Source dataset, raw POS transactions Parquet. Uses the ADLS Gen 2 linked service, points to the raw/post-transactions/folder, and expects Parquet format. Source dataset, product catalog Parquet. Uses the ADLS Gen 2 linked service, points to raw/product catalog/ expects Parquet format. Sync dataset, Synapse Fact Sales table. Uses the Synapse Analytics linked service, points to the fact sales table in the data warehouse. Sync dataset, error log CSV in ADLS. Uses the ADLS Gen 2 linked service, points to an error folder e.g. /errors/post-transactions/ expects CSV format. The orchestration pipeline, name. Pipe transform load fact sales. Parameters can accept processing date if processing a specific day's data. Activities, data flow activity. This is the core transformation engine. Sources within data flow, source POS. Reads from the raw POS transactions Parquet dataset. Source product, reads from the product catalog Parquet dataset. Transformations within data flow, derived column, POS data. Clean up transaction amounts, e.g., handle negative values, extract date components, calculate line item total. Derived column, product data. Standardize product categories, ensure product IDs are consistent. Join POS and product. Perform an inner join on product ID between the transformed POS data and product data. This ensures only transactions with valid product definitions are processed further. Conditional split, error handling, add a split. valid transactions stream contains all joined data. Invalid transactions stream captures rows from the POS data that did not join successfully, i.e., missing product ID or no match found, or any rows with identified data quality issues, e.g., line item total is 0 or negative after cleaning. Aggregate valid transactions. Group valid transactions by sale date, product ID, and store location to calculate total revenue, total quantity, and number of transactions. Syncs within data flow. Sync fact sales. Writes the aggregated valid transactions to the Synapse fact sales table dataset. The write method can be upsert if handling updates or append for daily new loads. Sync error log. Writes the invalid transactions data to the error log CSV dataset with dynamic file name incorporating processing date time. Copy activity for staging optional. For very large tables in Synapse, sometimes ADF might first copy data to a temporary staging table or external table location in ADLS, and then run a copy into command or insert into. Select from within Synapse using a stored procedure activity. This can be faster using Synapse's distributed compute. Alerting activity. An on-failure dependency from the data flow activity triggers a web activity to an Azure function, sending a notification about the failed transformation. The automation trigger. Type. A schedule trigger, e.g., daily at 5 o'clock a.m. after the ingestion pipeline completes. Or, for tight dependencies, an on-completion trigger could be created where pipe ingest POS transactions daily successfully finishing triggers pipe transform load fact sales. Outcome, raw sales and product data from the data lake are intelligently transformed, errors are isolated, and cleaned, aggregated sales facts are loaded into the data warehouse, ready for executive dashboards and advanced analytics. Scenario 3. Event-driven file ingestion and initial processing with decompression. The problem: an external marketing partner regularly drops compressed zip files containing customer feedback, surveys into a specific blob storage container in Azure. As soon as a new zip file lands, it needs to be immediately unzipped, and its contents, often CSV or TXT, should be moved to a separate, staged folder for further processing, and a message should be sent to a queue for an event-driven system. The solution outline. This emphasizes reactive processing and direct integration capabilities of ADF. Connections, linked services. Source Azure Blob Storage Link Service. Points to the main blob storage account where the zip files land. Staging Azure Blob Storage Linked Service can be the same as source if just different containers folders. Points to the staging area for unzipped files. Azure Storage Queue Linked Service to send messages to an Azure Storage Queue for downstream microservices. Data definitions, datasets. Input dataset, compressed feedback data. Uses the source blob storage linked service, points to the container and folder for new zip files, e.g., incoming feedback. Crucially, the format is set to binary to handle the zip file content without attempting to parse it. Output dataset, unzipped staged data. Uses the staging blob storage linked service, points to staged unzipped feedback. The format should be the expected format of the unzipped contents, e.g., delimited text if the internal files are CSV. Output dataset, queue message, uses the Azure Storage Queue linked service to send short messages. The orchestration, pipeline, name, pipe event unzip stage feedback. Parameters. The event-based trigger will automatically pass the file name and folder path of the newly arrived blob as pipeline parameters. Activities, copy activity, decompress and stage. Source. Uses the input dataset, compressed feedback data, dynamically referencing the file name parameter from the trigger for the specific zip file path. Sync. Uses the output dataset, unzipped staged data. Key property. Within the copy activity settings, under source options or compression, enable the decompress property and specify zip deflate as the compression type. This tells ADF to automatically decompress the blob file as it copies. Dynamic sync file name, the sync file path, e.g., @pipeline, parameters folder path / @replace, pipeline, parameters file name, zip, unzip CSV will be dynamically constructed to place the unzipped content. Web activity, send queue message, URL, set to the Azure Storage Queue API endpoint. Method, post. Body, a JSON payload dynamically constructed to include information about the unzipped file, e.g., at concat unzipped file. Pipeline, parameters file name. Path, staged unzipped feedback. This informs downstream systems that new data is ready. Error handling. An on-failure pathway could trigger another web activity to an Azure function to log the failure and the name of the problematic zip file for manual investigation. The automation, trigger, type, an event-based trigger. Configuration, configured to listen for blob-created events in the incoming feedback container of the source blob storage linked service with a filter for asterisk, zip files. Outcome, as soon as a zip file containing customer feedback lands in the designated blob storage folder, it automatically triggers the ADF pipeline. ADF seamlessly unzips the file, places its contents into a ready-for-processing folder, and sends a notification message to an Azure storage queue, initiating further automated steps in a microservices architecture. This is a common pattern for building responsive, serverless data ingestion pipelines. These scenarios illustrate just a few of the many ways Azure Data Factory can be deployed to build a streamlined, secure, and scalable data integration landscape. By understanding the core components and their interplay, you can adapt these patterns to solve virtually any data movement or transformation challenge your organization faces. Chapter 10. The Future of Your Data Journey. Advanced Topics and Next Steps. You've embarked on a fascinating journey through the world of Azure Data Factory. From understanding the foundational concepts of data integration to building intelligent pipelines, and from securing your data to orchestrating complex workflows, you now possess a solid blueprint for mastering your data deluge. But the world of data is dynamic, constantly evolving with new technologies, best practices, and challenges. This final chapter looks beyond the core functionalities we've covered, offering a glimpse into more advanced topics and strategic considerations that will elevate your Azure Data Factory skills and prepare you for the continued evolution of your data journey. 10.1 Embracing DevOps. Continuous Integration and Continuous Deployment, CI/CD. As your Azure Data Factory solutions grow in complexity and critical importance, manual deployment processes become a bottleneck and a source of errors. DevOps is a set of practices that combines software development, dev, and IT operations, ops, to shorten the system's development lifecycle and provide continuous delivery with high software quality. For Azure Data Factory, this translates into CI/CD, Continuous Integration, Continuous Deployment. Continuous Integration, CI. This involves regularly merging all developers' working copies to a shared mainline, automatically building the code, and running tests. For ADF, this means using a source control system, like Git in Azure DevOps or GitHub, to manage your ADF JSON code definitions. Every time a developer commits changes to the repository, an automated build process validates the changes, ensuring they integrate correctly without breaking existing features. Continuous Deployment, CD. Once changes are continuously integrated and validated, CD automates the release of those changes to different environments, e.g., from development to test, and then to production. For ADF, a CD pipeline would automatically deploy your linked services, datasets, and pipelines from your Git repository to your designated Azure Data Factory instances in various environments. Why is CI/CD critical for ADF? Consistency ensures that what's deployed to production is exactly what was tested. Speed automates deployments, reducing manual effort and deployment time. Reliability minimizes human error during deployment. Auditability provides a clear audit trail of who changed what, when, and where it was deployed. Rollback capability enables quick and safe rollbacks to previous versions if issues arise. ADF integrates natively with Git repositories. When you enable Git integration in ADF Studio, all your Data Factory artifacts become JSON text files, which are version-controlled in your repository. Azure DevOps and GitHub Actions provide powerful tools to build and release pipelines that automate the deployment process. 10.2 Maximizing Efficiency. Data Flow Performance Tuning. While we touched upon copy activity optimization, data flows, with their Spark backend, offer another layer of tuning opportunities, especially for very large datasets and complex transformations. Compute optimization. You can choose different compute sizes and performance characteristics for your data flow, e.g., general purpose, memory optimized, compute optimized. Selecting the right size based on your data volume and transformation complexity is key to balancing performance and cost. Partitioning. Data flow automatically handles partitioning internally across Spark nodes. However, understanding how data is partitioned, e.g., source partitioning, optimization that occurs through joins, and occasionally guiding it can significantly impact performance. You can use the Optimize tab within certain transformations, like join, aggregate, to choose specific partitioning strategies. Caching. For lookup operations or frequently reused sources, caching can dramatically improve performance by storing data in memory within the data flow cluster. Data skew. When data is unevenly distributed across partitions, some Spark nodes can become bottlenecks. Monitoring for data skew through the data flow sync statistics and repartitioning strategies can help alleviate this. Monitoring and debugging. The data flow debug session provides insights into data transformations at each step, allowing you to troubleshoot data quality issues and performance bottlenecks in real time. The Monitoring tab for a data flow activity run details the Spark plan and execution times for each stage. 10.3 Event-Driven Architectures and ADF. We explored event-based triggers for reactively starting pipelines when files land in storage. This is just one facet of a broader architectural pattern: Event-Driven Architectures, EDAs. Azure Event Grid, a fully managed event routing service that enables you to build EDAs. ADF can subscribe to events published by other Azure services, like changes in Cosmos DB or Azure Functions, via Event Grid and trigger pipelines accordingly. This allows for highly responsive and scalable data processing, reacting immediately to business events. Integrating with Azure Functions and Logic Apps, Azure Functions, used for lightweight, serverless custom code execution. As seen in previous chapters, ADF can trigger functions via web activities, and functions can, in turn, trigger ADF pipelines, e.g., via the ADF REST API. This allows for highly flexible integration patterns. Azure Logic Apps, a low-code, no-code workflow automation service. Logic Apps can consume ADF events, e.g., pipeline completion failure, and orchestrate downstream actions, e.g., complex notification workflows, updating other systems. They can also be used as triggers to start ADF pipelines based on events from hundreds of connectors, e.g., an email arriving, a tweet, or a HubSpot update. Combining ADF with Event Grid, Functions, and Logic Apps creates highly reactive, scalable, and resilient data processing solutions. 10.4 Integrating with the broader Azure data and AI ecosystem. Azure Data Factory is rarely used in isolation. It's a central orchestrator within a much larger ecosystem of Azure data and AI services. Azure Synapse Analytics. Often mentioned as a destination for ADF, Synapse is a comprehensive analytics service that brings together data warehousing, big data analytics, Spark, data integration, pipelines similar to ADF, and monitoring into a single environment. ADF pipelines can seamlessly integrate with Synapse, Spark pools, or dedicated SQL pools for data processing and warehousing. Azure Databricks, a highly optimized Apache Spark service on Azure. ADF frequently uses the Databricks notebook activity to run complex Spark jobs authored in Python, Scala, or R, extending ADF's transformation capabilities. Azure Stream Analytics Event Hubs. For real-time streaming data scenarios, ADF can pick up processed results from Stream Analytics or be part of a Lambda architecture where it handles the batch processing layer. Azure Machine Learning. ADF can train and score machine learning models using integration with Azure ML pipelines, transforming and moving data for ML workflows. Azure Purview, a unified data governance solution that helps you discover, understand, and manage all your data assets across your enterprise. ADF can register its data sources, pipelines, and transformations with Purview, contributing to a comprehensive data catalog and lineage view. 10.5 Looking ahead, the evolving landscape. The pace of innovation in cloud data services is incredibly fast. What new features might ADF gain? What emerging trends should you watch? Increased AI/ML integration. Expect more built-in AI/ML capabilities within ADF, possibly through new activities or enhanced data flow transformations that allow for common ML tasks, e.g., anomaly detection, sentiment analysis, without deep ML expertise. Enhanced data governance and observability. Stronger native integration with data quality tools, data lineage visualization beyond basic monitoring, and enhanced capabilities for tracking data movement and transformation for auditing purposes. Unified data platforms. The trend towards unifying data warehousing, data lakes, and data integration will likely continue, with ADF playing a central role in these converged platforms. Hybrid and multi-cloud dominance. As organizations embrace hybrid and even multi-cloud strategies, ADF's ability to connect to diverse environments will remain a critical differentiator. Low-code, no-code empowerment. The push for low-code, no-code solutions will continue to lower the barrier to entry for data integration, allowing more business users and analysts to build their own pipelines, while still providing powerful options for professional developers. Your continuous data journey. Mastering Azure Data Factory is not just about learning a tool. It's about understanding the art and science of data engineering in the cloud. The principles of efficient data movement, robust transformation, intelligent orchestration, and diligent security and governance are timeless. As new data sources emerge, business needs evolve, and technologies advance, your foundational knowledge of ADF will enable you to adapt, innovate, and continue to build sophisticated solutions that turn raw data into your organization's most valuable asset. Keep experimenting, keep learning, and keep building. Your data factory blueprint is now complete. The construction of a truly intelligent data future is in your hands. Further reading and resources. Microsoft Learn, the official learning platform for Azure, offering free modules and learning paths for Azure Data Factory, Azure Synapse Analytics, Azure Databricks, and other services. Azure Documentation, comprehensive and always up-to-date documentation for all Azure services. Azure Data Factory blog, stay informed about the latest features and updates. GitHub repositories, explore official Microsoft and community-contributed examples of ADF solutions and best practices. Microsoft certification paths, consider pursuing certifications like Azure Data Engineer Associate to validate your skills.